everyone, and welcome back after the summer break to the first BTSYM lecture. Today we're joined by Fabio De Carlo, who will be giving a presentation on the evaluation of the bearing capacity of fiber reinforced concrete sections under fire exposure. Before we do start, I will give a quick briefing on any emergency procedures we have. If there is a fire alarm, on hearing the alarm, you must evacuate immediately. Using the nearest exits, there's one at the back and one at the front here. You should not stop to collect your personal belongings and must not use the lifts. The alarms, there's no fire alarm testing today. It's tested every Friday afternoon. The fire exits, as I said, is at the front and the back. The assembly point is on the corner of Little George Street and Parliament Square, Storey's Gate and Prince Mews. You must remain there until one of the assembly points, until we're given a clear to come back into the building. Please do not leave your bags unattended at all times. If there is any first aid requirement, we can call upon at the reception. If you could please turn your phones, smart devices, electrical watch, anything that may disturb the lecture on silent or off, that would be much appreciated. Fabio is a postdoctoral fellow of the Department of Civil Engineering and Computer Science Engineering at the University of Rome, where he collaborates with the chairs of structural analysis and design, bridge design, and static of historic masonry construction. During the academic year 2018-2019, he has held the course of masonry constructions at the University of Cassino and Southern Lazio. His research activity deals with the following topics: modeling and analysis of masonry structures, with particular attention to the seismic strength and out-of-plane and in-plane collapse mechanisms, retrofitting of reinforced concrete and masonry structures with innovative material, service life of reinforced concrete structures suffering from corrosion of their reinforcing bars, behavior of reinforced concrete and fiber reinforced concrete structures under fire exposure, structural behavior of fire reinforced concrete elements with particular reference to tunnel lining segments and bridge slabs. His research activities is well documented in several national and international papers. So Fabio, the floor is yours.
Thank you. Good afternoon to all. Thank you, Rashik, for your kind invitation. It's an honor to be here. Here there is an opening slide with some happy images from Rome, from the university from which I come from. Maybe it could be an incentive to come to visit us. Coming back to our topics, my presentation of today deals with the evaluation of the bearing capacity of fiber reinforced concrete section without any traditional reinforcement under fire exposure. Fiber reinforced concrete is a composite material, as we all know, made by a concrete matrix in which fibers are dispersed. The presence of fibers within the matrix, the concrete matrix, has many important effects in the structural behavior, such as improving in cracking control, an increase in toughness of the material, an increase in impact and fatigue resistance. The brittleness characterizing the behavior of plain concrete can be get through by using fiber reinforced concrete. As we all know, in the last few years, the interest in using fiber reinforced concrete is growing because of its several advantages related to a reduction in terms of costs, not only the cost of the bare material, but also the labor cost, and an improvement in quality and structural performance. This is due to the possibility to partially or totally replace the traditional steel reinforcement. Many applications can be found in pavement construction, shotcrete, and in the precast industry. In this context, one of the most significant applications of fiber reinforced or structural concrete or fiber reinforced concrete is tunnel lining. Reinforced concrete tunnel linings have been traditionally cast in situ, but the development of the tunnel boring machines has led to the invention of the precast concrete segmental lining technology, which is nowadays one of the most promising applications of fiber reinforced concrete material. The use of fiber reinforced concrete allows to eliminate, to reduce the steel reinforcement. In these tunnels, the precast segments, as we know, are used as a reacting element by the tunnel boring machine during the excavation process. A number of large tunnels have already been built around the world with this technology. Reference documents for the design of reinforced concrete and fiber reinforced concrete structures are the Eurocodes and the FIB Model Code for Concrete Structure 2010. Since the mechanical excavated tunnels are more and more used in civil engineering, the FIB Commission first concrete structures started to a series of documents related to the use of fiber reinforced concrete in underground construction. For this reason, the FIB Task Group 1.4 tunnels decided to create the Working Party 1.4.1 tunnels in fiber reinforced concrete. The convener is Professor Meda from Rome, with whom I collaborated in preparing the FIB Bulletin 83, precast tunnel segments in fiber reinforced concrete. Maybe if they want to see later, there is a copy. And here there are some figures showing the motivation of this study, which is joined to the occurrence of fire events inside a tunnel. In order to improve the design of reinforced concrete and fiber reinforced concrete structure, we need a better understanding of the concrete behavior. A significant difference in the behavior of reinforced concrete and fiber reinforced concrete sections with respect to fire consists in the degradation of their mechanical properties. In the first case, so reinforced concrete section, the traditional steel reinforcement located at a distance from the external side of the section equal to the concrete cover undergoes to a rapid decrease of its mechanical properties. With reference to fiber reinforced concrete section, the degradation of the mechanical properties is less appreciable because the tensile resistance of the section is marked all over the portion of the section which is subjected to tensile stresses. In this framework, the evaluation of the bearing capacity of FRC elements is worth of interest and to the advantage of engineers looking for better and safer standard design standards. A proper assessment of the structural behavior of FRC elements is important as in design phases, for example, to extend the service life of structures, as in repair or strengthening of existing structures, for example, in case of rehabilitation after a damage occurred during a fire event. As well known, the heat transmission within an isotropic solid body with internal heat generation in aesthetic conditions is governed by the Fourier equation, in which lambda is the thermal conductivity, rho is the density of the material, C is the specific heat, T is the temperature, Q the volumetric heat flux, and T is the time. In the simplified case which we are interested, so in the with the simplification of one-dimensional heat transfer, in absence of heat generated within the body and constant thermal conductivity throughout the medium, the Fourier equation reduces to this second equation, in which alpha equal to the ratio between the thermal conductivity and the product of the density and the specific heat is named thermal diffusivity. In addition to this partial differential equation, it's necessary to specify the initial conditions and the boundary conditions. So the initial condition refers to the initial temperature distribution inside the section, while different boundary conditions can be set over the portion of the boundary surface of the section. And we have a prescribed surface temperature, for example, a prescribed heat input, a perfectly insulated surface, or a convection or radiation boundary condition. If complex boundary conditions or variable properties of the material of which the section is made are involved, the partial differential equation, the Fourier equation, cannot be solved with analytical solution methods, and we have to use numerical solution methods. These methods are based on the discretization of the section in a series of strips, and the partial differential equations is replaced by a set of algebraic equations in the unknown temperatures of the endpoints of the domain. Among all available methods, in the finite difference approach has been here used, and its starting point of the procedure is the identification of a layer of points in the space-time domain R, where X is the space variable, L is the length of the section, and T is the time, and T star is the duration of the fire events. The finite difference approach is based on in substituting the derivatives of the temperature, the second derivatives and the first derivatives of temperature, with the following differences. In case of temperature-independent material properties within the body, this expression gives the temperature at the point E at time j plus 1 as a function of the temperature at the points E plus 1 and E minus 1 at time, previous time, j. This numerical method is stable if this condition is satisfied, so if this parameter k is lower than 0.5. It's worth to underline that in case of homogeneous body but properties dependent on temperature, being lambda including the derivative, we can again set the equation of the heat transmission in simplified form by adopting a change in the temperature scale in which lambda 0 is convenient, is the thermal diffusivity at a convenient reference temperature T0, for example, the initial temperature inside the body. With reference to the examined case of fire inside the tunnel lining, we have to specify the initial condition and the boundary conditions. So the initial condition is assumed to be a constant temperature equal to 20 Celsius degrees. And regarding the boundary conditions, on the extradose side of the cross-section of the segment lining, a prescribed temperature has been applied, has been imposed, equal to 20 Celsius degree due to the presence of the soil. A combined convection and radiation boundary condition is imposed on the fire-exposed surface according to Eurocode 1. In particular, the net flux is determined by considering both terms related to convection and radiation. Two fire curves have been considered, the ISO A34 and the RWS fire curves. The first one, developed for general buildings and content, can be used since its energy content is similar to the ones obtained through fire analysis of tunnels and metro tunnels. The second one, the second curve, the RWS fire curve, typical of railway or road tunnels, was developed by the Ministry of Transport in the Netherlands, and it's based on the temperature expected during 50 cubic meters fuel tanker fire in an enclosed area. All the parameters are shown in the slide, the required parameters. And finally, an adiabatic condition is imposed on the two vertical sides of the fiber reinforced concrete section. Okay, in order to perform the thermal analysis, we have to define the value of the values of the three parameters of the thermal conductivity, of the density, and of the specific heat for the fiber reinforced concrete material. According to the Italian guideline, but there are also other guidelines. Pardon. The Italian guidelines is the CNRDT 200 for 2006. We can use typical values of plain concrete also for fiber reinforced concrete. And in this case, reference has been made to the Eurocode 2. The thermal conductivity is so determined between a lower limit and an upper limit defined from these two relationships. the density of the material is influenced by water loss, and it can be described by a multilinear law. The specific heat, also here, a multilinear law. This law is valid for both cases of calcareous and aggregate and siliceous aggregates of the mix. And in case of different values of the content of the moisture content, the function of the specific heat can be modeled with a constant value, C peak is named, depending on the moisture content, in the range between 100 Celsius degrees and 115 Celsius degrees, and by a linear decrease between 115 Celsius degrees and 200 Celsius degree. We know that the behavior in compression of the fiber reinforced concrete material is the same of the reinforced concrete one. The behavior in tension is instead characterized by means of the 3-point bending test, which gives the trend of the residual strength versus the crack mouth opening displacement, CMOD. And the fiber reinforced concrete material is classified through the characteristic value of the residual strength significant for serviceability condition, so FR1K, and by a letter from A to E, which gives the residual strength ratio equal to the ratio between FR3K and FR1K, where FR3K is the residual strength for a crack mouth opening displacement equal to 2.5 millimeters. For example, as we know, a 4C material is a material with an FR1K equal to 4 MPa and a value of FR3K included in the range between 0.9 of FR1K, so 3.6 MPa, and 1.1 times the FR1K, so 4.4 MPa. In order to assess the bearing capacity of the fiber reinforced concrete material, we have to define the constitutive law of the material in both compression and tensile branches. And according to, again, to the Italian guidelines and to the FIB model code, we can use a stress block constitutive law in both compression and in tension. So the behavior in compression is governed by the design value of the cylinder compressive strength, FCD, over a length equal to 0.8 time of the neutral axis X, while the behavior, the stress block constitutive law in tension is governed by the design value of the post-cracking strength for ultimate displacement, so FTUD, which is defined as the value of FR3K divided by 3. It's worth of interest to underline that the partial safety factors for the FRC material are equal to 1, since fire is an exceptional condition. Okay. With reference to the decay of the mechanical properties with the temperature, we can, as reported in the FIB Bulletin 83, we can make reference to the Eurocode number 2, which gives the dependence between the trend of the characteristic cylinder compressive strength, varying the temperature T inside the section, as the product of the characteristic value of the cylinder compressive strength at the room temperature, so T equal to 20 Celsius degrees, multiplied by a temperature-dependent coefficient named KFC. And here in this table there are the numbers, and this is the trend for both siliceous and calcareous aggregates. So the continuous line, siliceous, is located under the calcareous one, so here the degradation is more important. The same holds also for the tensile strength. We can, as reported again, the FIB Bulletin 83, we can make reference, for example, to the Italian guideline, which gives, again, the characteristic value of FR3 dependent on temperature as the product of the FR3, the characteristic value of FR3 at the room temperature multiplied by a temperature-dependent coefficient named KFT. In this slide is shown an example of the thermal field, so the result of the thermal analysis. On the left side, the thermal field at the ending time of the fire events is shown by means of a colored map with colors from red to blue, referring to higher or lower temperature values. Or in the right side of the slide, there is a representation by means of ISO curve. And in this graph, on the y-axis, there are the temperature values. On the x-axis, there is the depth of the section. And so this is the exposed side of the section in which the temperature values are higher. And this is the inside. These are the results for, in the case of a 0.3 meter high section made with a fiber reinforced concrete classified as a 4C and subjected to the action of the ISO curve, the ISO 8345 curve. Okay. The residual bearing capacity of the fiber reinforced concrete section is assessed by means of bending moment axial force interaction envelopes. Starting point of the procedure is the thermal analysis, which gives the thermal field within the fiber reinforced concrete section, varying the time T. So once we have fixed the time T in which we want to assess the bearing capacity of the FRC concrete section, the temperature values in all the points of the domain is known. So we can subdivide the section in a series of strips, N. Each one is characterized by a known value of the temperature and by the constitutive law of the material connected, related to the temperature in this point. So in this slide we have the two cases of sagging bending moment. So when fire acts on the side of the section subjected to tensile stresses, and the case of the hogging bending moment when fire acts on the side of the section in which there are compressive stresses. In these two schemes, we can see the degradation. I don't know if everybody is able to see because of the colors. For example, here in red, there is the tensile, the tensile constitutive of the material, and the fire is acting on the tensile side of the section. So here we can see the degradation of the FF2D, otherwise for the compressive constitutive law. So in the strips of the section in which we have higher temperature produce a higher degradation of the mechanical properties. So we can write two equations expressing the translational and the rotational equilibrium conditions of the fiber reinforced concrete section, in which NSC is the number of the compressed strips within the length of 0.8 of the natural axis, and NST is the number, the integer number of strips within the tensile part of the section. So the bending moment axial force interaction envelope is obtained by imposing a vector of natural axis and by evaluating the couples MN obtained with these two equations. Okay, let's see some result. This slide shows the bending moment axial force interaction envelopes of a 0.3 meter high section made at the room temperature T equal to 20 degrees. So there is no fire here. And for two types of material, a 50 for C material and a 40 for C material. So the behavior intention is the same, and in particular we have tensile strength equal to 4 MPa. What is changing is the behavior in compression, because it's changing the design value of the cylinder compressive strength. And we can see the difference in the bending moment axial force envelope. The same, in this slide, is shown the same, but the difference in the material consists in the tensile behavior. So the behavior in compression is the same. We have a 50 MPa of the compressive strength, and while the tensile strength of the fiber reinforced concrete changes from 4 MPa to 7 MPa. From this slide, we can see a marked influence of the compressive strength on the evaluation of the bending moment axial force envelope. We have a marked difference when we change the compressive law of the material in compression. Okay, in this slide, there is a superimposition of the bending moment, axial force interaction envelopes for, again, a 0.3 meter high made with this material and subjected to the ISO 834 fire curve for different time duration, so of the fire event. So at the initial time T equal to 0, so for the temperature of 20 Celsius degree, and for 4 durations of the fire events equal to 30, 60, 90, and 120 minutes. We can see the different decay of the bending moment axial force interaction envelope for positive and negative bending moment. In particular, the upper part of the domain refers to the case of fire acting on the side of the section where there are tensile stresses, while the lower part of the domain refers to the opposite condition of fire acting on the side of the section in which there are compressive stresses. And joined to the fact that we have seen before, we notice that this difference in the decay of the axial force bending moment interaction envelope, since the parameter already at the room temperature, the parameter which is influencing the bending moment axial force envelope is the compressive strength, and so the higher differences are found when fire acts on the side of the section where there are compressive stresses. Okay, here we make a comparison between the structural behavior of reinforced concrete section and fiber reinforced concrete section exposed to fire. So let us to consider two sections with the same value of the thickness, so 0.3 meters, subjected only to bending moment. The fire is acting on the tensile side of the section. The first section is made with this material, the fiber reinforced concrete 44C. The second section is made again with a concrete having a design cylinder compressive strength of 40 MPa, but there is a traditional steel reinforcement with a yield strength equal to 450 MPa. And these sections are equal in terms of ultimate bending moment at the room temperature, so T equal to 20 degrees. Both sections are subjected to the action of the ISO 834 fire curve. Here we can see some results in terms of ultimate bending moment of the fiber reinforced concrete section, varying the time of varying the fire duration. So we can see a degradation of the mechanical properties of the material and a connected degradation of the ultimate bending moment, varying the temperature. For sake of clarity, these values are the intersection points of the bending moment axial force interaction envelopes with the y axis, with the vertical axis in the upper part, which is the part of the domain related to the case of fire which is acting on the tensile part of the section. We make the same for the reinforced concrete section, but for this we have to introduce the degradation of the traditional steel reinforcement. For example, according to Eurocode 2, which gives the degradation of the yielding strength of the steel with temperature. So we know the temperature value at a distance from the external side of the section equal to the concrete cover. So we can know the temperature at this point. And we can associate the relative value of the design value of the yielding strength of the traditional steel reinforcement. And with this, we can evaluate the ultimate bending moment of the reinforced concrete section. In this slide, the results are superimposed by means of a graph in which on the x-axis there is the time, there is the fire duration. On the y-axis there is the ratio between the ultimate bending moment in presence of fire and the ultimate bending moment at the room temperature for both sections. So the reinforced concrete one with the dashed line and the fiber reinforced concrete section with the continuous line. We can see that for the case of the reinforced concrete section, the ultimate bending moment is initially slightly influenced by the fire events, because the temperature values inside within the concrete cover are not so high to produce a significant degradation of the steel, of the yielding strength of the material. But with increasing the fire duration, the temperature values within the concrete cover increases with a significant degradation of the mechanical properties of the material and with an almost linear degradation. With reference to the fiber reinforced concrete section, we see that the degradation of the material starts at the beginning of the fire events, but the degradation is lower than the reinforced concrete section because the tensile resistance of the section is not localized in the points in which there are the steel bars, the steel reinforcing bars, but it's smeared over a portion of the section which is subjected to tensile stresses. So there will be the strips more close to the external side with the higher temperature values. They will have a higher material degradation. But the inner part of the section, of the tensile part of the section, in which the temperature values are lower, this part will continue to resist with a tensile strength not so low. For example, at the end of the fire events, after 120 minutes, we found an ultimate bending moment which is about 2 times for the fiber reinforced concrete with respect to the reinforced one. Okay. In this slide are shown some results of a parametric investigation performed by considering a 0.3 meter high section with the 50 4C material, which is subjected to both fire curve, the ISO 834 and the RWS, and here there are the thermal fields within the section at the room temperature and for 2 values of the fire duration equal to 30 minutes and 120 minutes. We can see the difference from this and this one and this and this one. In the upper figure, to the right side of the slide, there is a superimposition of the bending moment, axial force interaction envelopes obtained for both fire curves, and we can notice that the MN envelope obtained with the RWS fire curve, as expected, they are always entirely contained within the ones obtained with the ISO curve. The RWS fire curve produces higher values of the temperature, but it refers to a fire with oil. In the lower part of the slide, in this graph, is instead shown a comparison, an equivalence of the same section subjected to two different fire scenarios. So, for example, the 0.3 meter high section subjected to the fire curve ISO for a time duration of 120 minutes is equal to the same section but subjected to the RWS fire curve for a lower duration of 60 minutes. They produce these two fire curves imposed with two different durations produce the same effects on the section. The same holds, for example, for 30 minutes duration of the RWS fire curve or the ISO curve imposed for 60 minutes. We have the last slide in which there is a comparison between section in terms of in which the decay of the material properties is expressed in terms of loss of thickness. So we have this section with this material, and for example, they have the same behavior, but we obtain the same behavior with a section at 0.25 meters high section without fire is equal to a 0.3 meter high section after 30 minutes of the RWS fire curve, or a 0.35 meters high section exposed to the same fire curve but with a duration higher, equal to 120 minutes. So it gives a measure of the thickness that we are losing, referring to a duration of the fire events. Okay, here we can give you some references where you can find these results I presented you today. So the FIB Bulletin 83, precast tunnel segments in fiber reinforced concrete, and this paper in the journal Materials and Structures, evaluation of the bearing capacity of fiber reinforced concrete section under fire exposure. Thank you for the attention. I hope to have been in time.
Yep. Thank you very much. We can take questions. We have a microphone at the front, I think. If there are any questions, yes.
How many? Sorry?
I'm interested to know the difference between polyfibre reinforced concrete and steel fibre reinforced concrete with respect to fire resistance.
These results are obtained in case of steel fiber reinforced concrete. Because the degradation of the parameters and the degradation of the materials refers to steel fibers.
What about polyfibre?
Have you done anything on polyfiber?
Polyfiber, for now, there is no indication of the degradation of the material properties with polyfibers.
The reason I ask is that I understand that polyfibre is defined as a fire-resistant material. On cross-track.
There's a difference between the macrosynthetic fibers and the microfibers, which is fundamental here. Fibre has to present of a structural reinforcement, which is obviously equivalent to a macrosynthetic fibre. This is, I think, not covered by this presentation.
No.
Microfibers, which are employed crossware and elsewhere, are in there for underscoring. But this is not a structural element. This doesn't cause any textual resistance, but basically one melting opens channels so that the steam can escape from the cross section and that's falling. Question myself.
Thank you.
The tools which you developed, Fabio, it's you're applying, for example, your finite element approach to establishing the temperature gradient throughout the cross section. From that, you derive the temperature dependent accurate parameters according to ideal flow 2 and further flows. Could that also be used to work out, say, the temperature-induced strain distribution of concrete, so that you not only capture the loading, the resistance side, as you did right now, but also the loading side?
Thermomechanical analysis, you mean?
Because obviously you're getting a strain distribution as well, so a delta in compression and a delta in bending moment from the fibre itself.
For the strain?
Sorry?
The strain?
Yeah, from the strains. So I haven't seen that in your presentation, which was focused on the resistance side. So the loading aspect follows to an extent the same rules. Is it planned or is it conceived to introduce the loading aspect as well based on the same tools?
Yeah. In fact, we wanted to introduce also the loading to make a thermomechanical analysis. For now, we assume that these aspects are divided, and we can evaluate the action and the bending moment and axial force, and then to make a verification of the safety in terms of ultimate bending moment. But we are able to do this because we consider a stress block distribution, so it's not joined to the strain.
Really nice step by step.
Yes, sure.
Very useful, thank you.
Thank you.
Yes.
Is that, you've done your analysis, are they backed up by some tests, some fire tests? Some fire tests
We didn't do tests. But in our laboratory, and also we collaborate with other laboratories in Italy, we have done tests for spalling.
Yeah, all I'm saying is you assume the resistance there, so if you've done the test, then you can go
verify
whether this resistance is
in the slide there are also the references I didn't say to you of some papers about the mechanical properties assessed by means of experimental tests. Maybe if we can, or maybe they have the slides.
Yep.
Yeah. So Felicetti is cited in the slide. There are also tests on these, on the mechanical properties of the material.
What I'm saying is, if you assume, follow your approach that you have certain resistance after the fire, then if you have done a test, you could
Verify.
smash the bomb and see whether this is real or overestimate or underestimate. So that's must have this test being done or schedule or run.
Yeah, are there any future plans for any testing or?
Maybe we would like to do tests. Maybe I don't know if we will be able to perform fire tests. Now we are doing other types of experiments in our labs.
I've got a question, might be an easy one. Could a similar analysis be carried out on SCL lining, sprayed concrete lining, rather than segments that have been cast?
A segment.
Can a similar analysis be carried out for sprayed concrete lining?
For?
For sprayed concrete line, shotcrete?
Shotcrete. Yeah. Okay. It should work the same.
Do we have any questions before we wrap up? Nope. Okay, could we get the next event slides, please? So on Thursday, 19th of September, there is a BTSYM workshop held at the ICE on tunnel waterproofing that will be delivered by Sika. If you'd like to join the workshop, the details can be found on our social media, as well as our emails going out through the ICE and the BTSYM. The workshop itself is from 2:30 onwards to 5:30. The next BTS evening lecture is on Thursday, the same day, 19th of September in the evening, with the title of Thames Tideway West, the design and construction of Hammersmith Connection Tunnel. That will be from 6 o'clock onwards. Next slide, please. My last BTSYM evening lecture on the Thursday, 7th of November, and that will be NATM in hyperbolic conditions. The exact title will be confirmed near the date. Again, that's on the 7th of November. Next slide. On the same day, we will be holding a short AGM. So if you would like to join the committee and get involved with the BTSYM, whether that's in organising professional development, such as the lectures and workshops, getting involved with the social side of the BTSYM or the schools and universities, we will be sending out a link on our social media and emails that you can join, how to join and what the different departments do. So please do look out for that. And I believe that is the last slide. Yeah. Okay, so what remains is to thank our speaker today, and hopefully we'll see you downstairs in the bar. Thank you very much.